Today we're going to talk about time-independent perturbation theory. Now this is going to be part of the course where we're talking about approximation methods, so it's probably good to stop and why are we doing this? Well, we've already studied many of the quantum systems that can be solved exactly. The hydrogen atom is a perfect example. We can solve the hydrogen atom, but once you get to larger atoms, it becomes very, you can't solve these things exactly. Furthermore, many of the systems that we've looked at are only approximations of real systems. And so we're going to need approximation methods in order to study a wider range of systems. And in fact, this is what you're doing a lot of times with quantum systems, is finding different ways to find approximate solutions. So this is a really important part of the course. We're going to start with perturbation theory. And perturbation theory is basically, the idea is we're going to take a system we already know and we're going to add a small perturbation to it. Now, one thing that's really tricky is just the nomenclature, and unfortunately, it's not consistent for between textbooks. So here we look here. This equation is the Schrdinger equation that we've already solved. And so that 0 is telling us it's for the system that we've already looked at. And so we have some Hamiltonian, and we found a complete set of eigenfunctions, psi n 0, and a complete set of eigenvalues, en 0. The n is the number of those, right? So for instance, the infinite square well, we looked at that and we found that it had an infinite number of eigenfunctions with eigenvalues. That's a good example. We'll do some examples with that later. And we're going to want to find the new eigenfunctions and eigenvalues for the new perturbed Hamiltonian. We won't use any zeros for that one there. So this is the system that we're sort of trying to look at. And in general, what we'll look to do is to write this new Hamiltonian as a sum of the Hamiltonian that we know really well and a new one, h prime, where h prime is the perturbation. So first, it's really important the perturbation is going to be small. So this will only work if it's a small perturbation. The subscript 0 always identifies the unperturbed quantity. So like I said, this can be really confusing. We're going to try to clear it up, but it is tricky. And another thing that's really tricky is this delta. So this delta is something that we put in, and you can assume that it's some small number, whatever, but basically it's literally just a dummy variable placeholder to help us sort of track the different orders in the power series that we're going to set up. So eventually we're going to set it equal to 1 and just sort of erase it and get rid of it, and that's also super confusing, but it's really just there to help us sort of keep our thoughts together as we're putting this theory together. So our new Hamiltonian is just that one we just had over here. And again, our goal is to go through and find the new eigenfunctions and the new eigenvalues. And so here we're going to make those a power series in terms of these deltas. So again, like this. So this is the first order, the 0th order, which is the solution without the perturbation, the first order, the second order, so on and so forth. And for each order, you get another factor of that lambda. Now, so those superscripts are the order of the correction, and the subscript is the number of the particular eigenfunction. So like the n equals to 1 state for the infinite square well, something like that. And we're going to find that pretty much for us, we're going to look at the sort of only first order corrections to the eigenfunction, and then over here, the first order and the second order corrections to the energy. Will be what we'll look at here. You can go higher, but in general, again, we're trying to find, we're dealing with perturbations that are small, and so you only need to go so far in these sums to hopefully get a decent answer. So this is kind of rough, but what we're doing here is we're writing out the first couple of terms for all these sums. So I'm taking my Schrdinger equation, so this guy here, and I'm writing out for the eigenfunction this sum, and for the eigenenergy this sum over here. And so we get this thing here. So again, we're writing our Hamiltonian as two pieces: the original Hamiltonian of the system that we know and love already, and the new perturbation. Here's my eigenfunction. Here's my other eigenfunction, and here's my eigenenergy. Now down here, I've collected all these sums, so you should just go through and make sure that this makes sense. And the way I've organized it is there's a few terms. There's one term that has no delta, I'm sorry, lambda. There's one term that has two pieces that have one delta here. I'm sorry, lambda, and then two pieces that have lambda squared, and the same thing for the other side of the equation. So we just basically went through and multiplied all this stuff together. So there's one term, h0 times psi 0n, that's this guy, check. H0 times lambda psi n1, h0 lambda psi n1. You'll find all the pieces in there. So if you want to stop here and just sort of double check that, please go ahead to make sure that this makes sense. We're just writing out the differential equation in basically a power series form. And the reason we do that is we're going to collect the different powers of lambda. And so here's that lambda equals to 0, which again is just our original statement of our original Schrdinger equation of that system that we love and know from some point in the past. And then this will be our first order equation from this power series, and our second order. So these are what we're going to use to go through and develop our theory. So we're going to start by taking this first one here. And again, all that is if you go back to that other page, is I basically, for the, lambda equals 1, I just took this guy and equaled it to this guy. So what we can do is go through and find the like powers of lambda and equal the terms in just those. And this differential equation, basically the terms for each power of lambda should equal to each other. And that's the reason, again, why we have this lambda here as this placeholder, just so we can sort of keep track, right? And so basically, this guy is a first order term, this is a first order term, and so when I multiply those two guys together, I get a lambda squared, making a second order term, so on and so forth. And so we take this equation here, and so let's start with this guy, this guy right here, and write it out. And what we'll do is we'll write it out in Dirac notation. So this is that same equation I just had, like on the right hand side, it's h0 psi n1, h prime psi n of 0. That's what we had over here, h1 psi n1, h prime psi n0. And just putting in Dirac notation, that's a little bit more helpful. And then what I'm going to do is I'm going to multiply both sides by the bra psi n0. So again, this is one of the eigenstates that we know and love from whatever system it is that we're talking about. Now this side over here, right, here in these terms, you're sandwiching a constant in between these bra and ket, and so you can just pull those constants out. So I'll pull this guy out, I get en, those two pieces. Here, it's really nice. When I pull the en1 out, these guys are orthogonal to each other, right? These are just the original, it could be like the n equals 1 state of the infinite square, well, whatever, but I know that right there, this idea of psi n0 should be 1. So I get rid of that. That goes away. And now over here, we're going to do some trickery to it. And what we're going to do is, I'll go back, is we can have this, since our h0, right, this is a Hamiltonian, it is a Hermitian operator, I can have it act to the left on the bra. And when I do that, I'm just going to get the original energy, 0, from our original Hamiltonian. So I get that over here. And so now we see what's this piece and this piece are identical, so we can get rid of those. And we end up here with our equation, which again, in the books they'll say is probably one of the most used equations in quantum mechanics, so we should stop and just reflect on that for a second. But what is this? This is the first order correction to the nth energy eigenvalue. And what it is it's got the form of a matrix element. It's basically the expectation value, if you will, of h prime. And so for most of the problems we're going to work on, this will be our starting point. We'll sort of start, okay, let's find the first order correction of the energy and see what we can do with that. All right, so let's work on finding the first order correction to the wave function. So I do that, I take our first order correction equation and I'm going to rewrite it so that the terms with psi n1 are on one side and psi n and 0 are on the other side. So if you want, pause and make sure that makes sense where I got that. The next thing is I'm going to assume that the correction to the wave function psi n1 can be written as a linear combination of the eigenfunctions from the unperturbed Hamiltonian. Again, this is the system that we've already looked at For example, the infinite square well. Okay, we know that these eigenfunctions are complete, and so you can express anything in terms of those. Now, the one thing we're going to do here is that we're not going to include the nth term. All right, and so here we're finding the correction to the wave function. Again, this is the first order correction of like the nth wave function. So like for an infinite square well, that's like the n equals to 1, n equals to 2 state, something like that. We're not going to include that state. Basically, it's just easier to not include it, and we can get away with it. And at the end of all this, I'll talk a little bit about that if you're interested. And so what we do is we then basically plug this sum in over here. So we get H0 minus En0, the sum of the Cmn pieces like that. And then again, so now we've got these functions here that we know really well. And so that is good. And this piece over here will just be written out like so. Now, what I'm going to do is I'm going to then take this operator and attack it over in here, right? You can think about it, this is basically just two terms together, and so what we can do, we should possibly specify that's m equals to n, is basically move that sum out front there. And then so what this does is, since these are the actual states of this guy, then if I operate on here, I just get this thing back times that eigenfunction. And so here we get this term here, which is going to be something that we'll be working with a lot with these kind of things. And as usual, what I'm going to do is I'm going to write this in Dirac notation because it'll just be easier for us to think about it that way. And so I'm almost done here. What I'm going to do is I'm going to multiply then both sides by the bra of psi L of 0, since I can multiply that if I want. And so I'll get this here. So these guys are all constants. So the operator, so the bra can just slide right in through all these guys here and just be written as psi L 0, psi M 0. Now here it's a little bit more complicated, so I'll write it out. So we can't just slide it through because this is H prime as an operator. And so I'll write it as psi L 0, H prime, psi N of 0. And then it'll be plus, we can actually, this is a constant, so we can just pull this out. So plus En1 psi L0 psi N0. So now what we can do, let's just make sure that we know that clear this is an N over here, is okay, so if we do this for L equals to N, we get the same thing we just got. We get the first order correction in energy. So we've done that. So let's do this for L not is equal to M. And so what that means is over here, this just goes straight to 0. So the left-hand side is just going to be this particular piece here. So again, these, whatever, we don't know what these are, but they're not the same state. And then here, if I'm doing this sum, if we know that L is not equal to N, then basically what it's going to do is it's going to, this term over here, this inner product will only be 0 when L is equal to M. And so we come out with the term, looking kind of like this. It'll take out it'll find the Lth term. So e to the L0 minus e to the N0 times the Lth coefficient. And so we've basically then found our particular coefficient over here that we want. So the C to the L to the nth coefficient is going to look like this here. If I clean it up a little bit, psi to L0, H prime, psi to N0, and then just to get rid of that negative sign, I'll switch the order of these energies over here in the downstairs part. And so this is the coefficient we want to find. And once we find that coefficient, then it's just a matter of expressing it in terms of these here. So then we can take this. So we just found the CLN. Now it's customary to write this in terms of an M. And so our first order correction to the wave function will be a sum, like so. And we're just going to basically plug this in, changing any L's to M's, and we get something like this here. right? And so what is this? So this is the correction, the first order correction to the nth eigenstate, and it's going to be this matrix element of, again, H prime is our unperturbed Hamiltonian, and you're dividing by the energies of the unperturbed Hamiltonian, the subtraction of two of them. So this is why it was important that we didn't include that one n equals to n piece, because if we did that, we'd have n equals en0 minus en0, and we'd have a problem here. We're going to see that if our system has degenerate energy values, so that where the energy is the same, then we're going to have a problem anyway, and we'll have to deal with that separately. But for now, we have this, and we won't talk about that. So we'll deal with systems that are non-degenerate for a while. And finally, we're going to look at the second order energy correction. And so if you go back in the presentation, we had the equation, which was our lambda equals 2, so our second order equation. So I've written that out. I put it in Dirac notation, and just like before, I multiplied both sides by psi n 0. And so you found out that over here, the psi n 0 was basically that inner product over here is equal to 1. And so we've got more terms than last time, but we'll see that a couple of them will cancel. And so again, because this is a Hermitian operator, I can attack it over here. And so that'll give me En0. And when I pull that constant out front, I'll get this guy times that guy, which is exactly this same piece over here. So this piece and this piece will cancel out. So that's really great. Now this piece over here has sort of a subtle point. So this piece is basically, this is the key part of that piece, right? And we just expressed the fact, if you look over here, that psi n of 1 is equal to a linear combination of all of the psi m zeros except when m is equal to n. And so what will happen then is if I look at this here, this guy here, I can express this as a, so m not equal to m, the sum of psi n 0, and then this would be psi m0. And of course, these are eigenstates of the unperturbed Hamiltonian, so they're orthonormal to each other. And so because we don't include the term when m equals to n, this just goes to 0. So another nice artifact of that decision we made. And so what this leads us to is that our second order energy correction is going to equal this thing right here, which of course, as we just discussed, we can write this out as a sum, like over here, for instance. I forgot the cm to the n terms, but it's the same sort of thing over here. So we can just express this out. Again, this psi n to the 1, I can express it out over here as a sum. So I'll just write it as a sum, m not equal to n, psi n 0, h prime, and of course, what we'll be multiplying these by then would be our coefficients c, m, n, times, again, the eigenstates of the unperturbed Hamiltonian. So this is a constant. I can just pull this out front, and we just solved for it. And so when this is all finished, it looks like this right here. So we'll get this beast right here. All divided by all right. So again, if you go back just before our wave function, we had that order. It was psi m0, psi n0 over the difference in energies, and so I just plugged that in. Here's psi m, psi n over those difference in energies, and it just works out that this piece over here is the complex conjugate of that. And so this is our expression. You can write this out, of course, just by taking the absolute squared of this piece here. And so when we're all done then, basically here's our results for time-independent perturbation theory. So again, we're trying to find the first correction to our eigenfunction and the second two corrections to our eigenvalues. And the equations look like this here. So that second correction to the energy, again, that you can write this as the just the complex conjugate of this piece here. And so it depends on, all these depend on the perturbation Hamiltonian and the unperturbed wave functions. All right, so now let's go and try to do an example, which I'll do in a separate video because this one's getting pretty long.